All right, let's talk about the invisible architect of, well, everything. It's the force that makes an apple fall, but also choreographs the dance of entire galaxies. We're talking about gravity, of course. And our entire understanding of this massive concept, it all kicked off with a surprisingly simple question.
So here's the big question. And it's so simple, it's almost a kid's question. It's the exact same puzzle that none other than Sir Isaac Newton himself was chewing on. I mean, think about it. An apple falls down, straight down, no doubt about it. But the moon, it just stays up. How is that possible? How can the same force be responsible for two things that look so completely different?
For the longest time, people thought these were two totally separate things. What happens down here on Earth was, earthly physics. And what happened up there in the sky, well, that was the heavens, perfect and governed by completely different rules. The absolute genius of it all was realizing, no, wait a minute, they're connected. They are two sides of the very same cosmic coin. And that's the mystery we're going to unravel today.
Okay, so how do we start to crack this cosmic puzzle? Where's the first clue? Well, funnily enough, it's not by staring up at the moon. It's actually by looking at something much simpler, the basic physics of just moving in a circle.
I want you to picture this. You've got a stone tied to a string, and you're swinging it around your head. To keep that stone from flying away, you have to keep pulling on the string, right? You're constantly applying this force that's pulling it towards the center, towards your hand. And what happens if you let go of that string? Whoosh! The stone flies off in a perfectly straight line.
So that center-seeking force you're applying, it actually has a name. It's called centripetal force. And don't let the fancy name fool you. It's not some new mysterious force of nature. It's really just a job description for whatever is doing the pulling. In our little experiment, the tension in the string is the centripetal force. So that leads us to the billion-dollar question, doesn't it? What's the invisible string holding onto the moon?
Well, the string holding the moon, it's Earth's gravity. And this is the absolute key, the big aha moment. The moon is falling towards Earth. It's falling all the time, just like that apple. The big difference is that it also has a tremendous amount of sideways motion. So as it falls, it also moves forward, and it just keeps missing us. It's in a constant state of falling around the Earth. And that beautiful path it traces, that's what we call an orbit. If gravity wasn't there, playing the part of that string, the moon would have been long gone, flung out into the darkness of space ages ago.
Now, let's be clear. Newton didn't just pull this idea out of thin air. You know that famous saying about standing on the shoulders of giants? Well, he really did. And one of the biggest giants he was standing on was an astronomer who had already, basically, written the traffic laws for the entire solar system. And that man was Johannes Kepler. This guy was a brilliant German astronomer who spent years, and I mean years, just crunching the numbers. He was looking at incredibly detailed data on where the planets were at different times. Now, he had no idea why they moved like they did, but he was the first person to figure out the exact mathematical rules for how they moved. He basically handed Newton the clues on a silver platter.
So, Kepler came up with these three fundamental laws. First, and this was a huge deal, he discovered that planets don't orbit in perfect circles. They move in ellipses, kind of like squashed circles. This completely shattered the old ideas about the perfection of the heavens. Second, he figured out that planets don't move at a constant speed. They actually speed up when they get closer to the sun and slow down when they're farther away. And third, he found this absolutely beautiful mathematical relationship between how far a planet is from the sun and how long its year is. He didn't have the why, but man, did he nail the what.
So if Kepler laid out the entire scene of the crime, describing exactly what happened, it was Newton who walked in, looked at all the evidence, and pointed directly at the culprit. He was the one who came up with a single, incredibly elegant rule that explained everything, from the apple falling from the tree to the planet circling the sun. And this, right here, was the game changer. You have to remember, back in Newton's day, everyone just assumed that Earth and the heavens were two different realms with two different sets of rules. Newton's big idea was to say, nope, that's wrong. The laws of physics are the same everywhere. They are universal. That means the force yanking the apple off the branch is the very same force holding the moon in its orbit. And apparently, this was the question that just wouldn't leave him alone. He thought, okay, if gravity can pull an apple from the top of a tree, why would it just stop there? Surely it reaches the tops of the highest mountains, right? So why not higher? Why not all the way to the moon? Just following that one simple train of thought to its logical conclusion, well, it was about to change the world. And here it is, the big reveal. The answer, all wrapped up in one of the most famous and powerful equations in all of science, the Universal Law of Gravitation. Now, I know equations can look a little scary, but the idea behind this one is actually incredibly simple. It just says that the gravitational force between any two objects in the entire universe depends on only two things: how much stuff they have and how far apart they are.
So let's just break that down real quick. First up is mass. That's the m's in the equation. The more mass something has, think a huge planet like Jupiter versus our Earth, the stronger its gravitational pull. More stuff equals more pull. Simple. But the second part, the distance, is the really cool part. The force doesn't just get weaker as you get farther away, it gets weaker by the square of the distance. So if you double your distance from something, the gravity doesn't get half as strong, it drops to 1/4 of its original strength. This little detail, this inverse square law, was the magic key that unlocked all of Kepler's laws.
And look, this amazing law isn't just for giant planets and moons. It applies to literally everything with mass. That includes you, it includes the chair you're sitting in, the device you're watching this on. So let's bring this cosmic law right back down to Earth and talk about how it affects us. And while we're at it, let's clear up something that confuses a lot of people.
Okay, so here's the deal. Mass and weight are not the same thing. Not at all. Your mass is, simply put, the amount of stuff you're made of, your atoms, your molecules. That number never changes, whether you're standing on Earth, jumping on the moon, or floating on Mars. Your weight, on the other hand, is just a measurement of the force of gravity pulling on your mass. And because gravity is different in different places, your weight changes depending on where you are.
Here on the surface of the Earth, that gravitational pull makes things accelerate downwards at a very specific rate. We call it g, and it's about 9.8 meters per second squared. But here's the really wild part. That rate of acceleration is the exact same for everything, no matter how heavy or light it is. And this, of course, brings us to that legendary story about Galileo. Way before Newton, he supposedly climbed a leaning tower of Pisa and dropped two different spheres, one heavy, one light. And what happened? They both hit the ground at the exact same moment. Now, ignoring air resistance, why does that happen? Well, it's pretty neat. Gravity does pull harder on the heavier object, for sure, but that heavier object also has more inertia, meaning it's harder to get moving. The two effects cancel each other out perfectly. Okay, so we've established that gravity is everywhere, it's relentless, and it's always pulling things together. So that raises a really interesting final question. If gravity is always pulling us down, how do we ever get up? How does anything ever escape?
You know this from experience, right? The faster you throw a ball into the air, the higher it goes. But eventually, gravity always wins and pulls it back down. So, what if you could throw it so fast? Is there a magic speed where gravity just doesn't win? Where it just keeps on going and never comes back?
Well, the answer is yes. There absolutely is a speed like that, and we call it escape velocity. It's the minimum speed an object needs to completely break free from a planet's gravitational pull and just coast away into space. It's the cosmic speed limit that every single rocket has to break to leave Earth.
And for our planet Earth, that magic number is a staggering 11.2 kilometers per second. To give you some perspective, that's fast enough to get from New York City to Los Angeles in about 6 minutes. It's an absolutely mind-boggling speed, and it really shows you just how powerful the force is that's pinning us to this planet right now. So there you have it. From a simple falling apple to the moon tracing its path across the sky, from Kepler's planetary laws to the incredible speed needed to escape our world, it all comes down to one single universal rule. It's a pretty amazing reminder that sometimes the biggest secrets of the universe are hiding in the most ordinary things around us. It just makes you wonder, right?